Lecture 8.4, the direction of the magnetic force. We've just finished with the magnetic force magnitude. Now we look at the details of its vector nature. And it's beautiful. Right-hand rules are really fascinating, especially with magnetic forces. The magnetic force is, as we've already written here, it says here that the magnetic force is equal to the charge times the velocity across the external field of the magnetic field. If we're only interested in the direction, then we really need to focus on the velocity across the magnetic field. And the one thing you want to pay attention to is this. Charges always wrap themselves around the magnetic field lines. So when you're drawing a picture, this is what you want to be thinking about. How are they wrapping themselves around the magnetic field lines? In certain situations, they can't. But that's what the right-hand rule is going to tell us. We use the right-hand rule, which I give the acronym of RHR, to visualize the vector nature of f of b. As a reminder, a vector has two parts. It has the tip, so if you're looking directly at the tip of the arrow, it looks like this, like a little bullseye, if I could say that. So it has a tip and a tail. So when I look at the tail, we imagine that we're looking at feathers. And so we're seeing the crossing of the feathers on the back. These will tell us when a vector points into or out of the screen. So in other words, if I have a vector that looks like this, and what I'm seeing here is that I see this bullseye. This tells me that the vector points out of the screen. So it's pointing right at us. And so when we're looking at this, we say, yep, that's the tip that we're actually seeing of the arrow. On the other hand, if I see something like this, across, then what we say here is that the vector points into the screen. So it's pointing away from us. Therefore, we're seeing the tail end of that vector. I have a tendency to use two right-hand rules, and there's many right-hand rules, but I only use two. There are two right-hand rules that I like to use. Actually, there's three, but for right now, we only want to look at two. There is method one, and it turns out that we use single fingers. Single fingers and a thumb, that is. And there's method two, that here, what you're seeing here is that you're really using the whole hand. Now, what I'm going to do here, as you'll see, so I want to organize these two methods in a single table. And it goes something like this. If I use method one, I then define my velocity with my index finger. I use for the magnetic field, I use my middle finger. And in this situation, the magnetic force is in the direction of your thumb. Now there's a second method that's written like this. So this is a method two. And I'll say that in method two, that's probably the one I use the most. So my velocity is the direction of my thumb. My magnetic field is all of my fingers. So I should say all four fingers. And then finally, the magnetic force is actually the palm of my hand. Now, I sketched these images, but I found that I was spending too much time on them, so I just copied them. I just drew them beforehand, and this is what I'll use right here. So I just did this beforehand so that I wouldn't spend so much time drawing them in front of you. So let's organize these tables here. So here's the way I look at it. I have a magnetic force that's going to look something like this. So in this situation, if I look at my thumb, that's going to be the direction of my thumb. And then I have a velocity. that velocity points in the direction of my index finger, and then my magnetic field points in the direction of the magnetic field. The same thing happens here, but now the orientations is different, but I'm still trying to form a right hand coordinate system with my fingers or hands. So then I'm going to say that this direction, the thumb direction, is the direction of the velocity. The magnetic field points in the direction of my fingers. And then finally, the direction of the palm is the magnetic force. So that's what we want to practice right now. So let's start thinking about this and how we want to look at this thing. So the first thing here is that as soon as someone says right hand rule for magnetism, this implies we are dealing with positive charges. That's what it means. Now, if we're dealing with negative charges, which we'll talk about a little bit later, you could use the left-hand rule, which is what I typically do, or if you use the right-hand rule, you got to add a minus sign. Either way, we'll encounter this here in a little bit. So now what I'm going to do is I want to set up a series of questions. So the first question is this. What are the directions? You know what? I think I want this big. Of the unknown variables. And in this case, we're really talking about what is the direction of the magnetic field? What is the direction of the velocity? Or what is the direction of the magnetic field? So we're going to use the right-hand rule, so we automatically think in positive charges. So let's look at three images, and then, but they'll be in a lot of detail. So here's our first one. So what is the direction of f of b? And the only thing that we're given is we're given this scenario here. We're going to be given that we know the velocity direction, which is pointing like this, right? So this is my velocity direction. And we also know that the magnetic field is pointing that direction. So the question is, which direction is the magnetic force? And what we want to look at is we want to look at images of each of these right-hand rules. And so I took pictures of my hands to try to set this up. So let's start with method one. So method one is the finger method. So if I come in here and I paste this guy, here's my hand. And what you're seeing here is that this is the index finger right here. So if I look at the index finger, that means that this direction is the direction of the velocity. So if that's the direction of the velocity, which direction is the magnetic field? Well, look at my middle finger. It's pointing downwards like this. So that's the direction of the magnetic field. Now it's hard to see because of the angle, but my thumb is actually pointing to my right now. So that's saying here that the thumb here is telling me that this right here is the direction of the magnetic force. So picture-wise, I'm saying something like this. I have a velocity. And I know the velocity is coming out of the board. I have a magnetic field pointing down. So according to the right-hand rule, that tells me I have to have a magnetic force for a positive charge to be to the right. Now, let's do it with method 2. See if that makes a little bit more sense. So now we're looking at method 2. So if I insert this image right here, here's what I have. And you'll see why I like this. This forms a better coordinate system with my hands. So here's my thumb. My thumb is what? The direction of the velocity. Look at the direction of the magnetic field. It's with my fingers. So then my palm, you could see here, is then going to be perpendicular to all of this. And this becomes very important, that perpendicular direction. So I'm going to move this down here a little bit here. But one of the things that we said here is that charges wrap around the magnetic field. So what does that mean? Well, I can see the magnetic field is pointing down. So let's draw the magnetic field. So these are the magnetic field lines. And we know that this guy is pointing down. Now, those magnetic field lines, the charge has to either go counterclockwise or clockwise. So then pick one point that makes sense. We know that the force has to be to the right, and it's got to go around the magnetic field lines. So then I'm going to come in here, and I'm going to say, this right here is my velocity, and that velocity is pointing out of the page. So what is that magnetic force going to do? Well, it's going to make it wrap around. In other words, I'm going to see this guy wrap around the magnetic field lines like this. So from our viewpoint, we see that this is going in what direction? The counterclockwise direction. Now, if we were to be looking straight from the top, so if we had a top view of the situation, look what we would see. We would see that the magnetic field lines would be pointing they would be pointing down. That looks like this. Now what I'm seeing is that I'm seeing this. Here is my little charge right here. But that little charge now is moving like this. So what's that magnetic force doing? It's pushing it in that direction. That's probably a bad way to draw it, but it's doing this. So as it's doing this, what's it going to do? It's forcing these guys to now start to move around the fields like this. It's making it rotate around. That's what the right-hand rule is showing. Now, one of the things that we should look at is that we should also look at this mathematically. So if I look at this mathematically, what am I actually seeing? So mathematically, we have to define a coordinate system using the right-hand rule. Now that coordinate system is arbitrary. So this is what I'm going to do. I'm going to say that I'm going to pick my coordinate system where this is the positive x direction. So then I just start setting up my right-hand rule here, and my right-hand rule says if that's the case, then I have no choice but to call that y, and I have no choice but to call that plus c, and this is going to be plus y. So now let's apply to our situation. In our situation, you can see here is that the velocity now has to do what? It has to point in the x direction, right? It's pointing in the x direction. Look at the magnetic field. The magnetic field is pointing not in the y direction, but in the negative y direction. So then this tells me that B here is going to be minus B in the y direction. So what does the magnetic field tell me then? The magnetic field, according to the right-hand rule here, then says that this has to equal the charge times the velocity crossed with the magnetic field. But we have vectors. So what's the vector? Well, you can see here is that this has to be what? It has to be QV x hat, and then we're going to cross this with the magnetic field in the negative y direction, which then tells me that this guy has to then be minus, let me keep my minus there, so it's got to be QV B, and then I have to do I have minus x hat crossed y hat, and this turns out to be minus z in this case. So that guy is the minus z direction. So in other words, we could then say that the magnetic field force, excuse me, is then going to be minus QV B in the z direction. And this guy is the magnetic force. That's what this guy is telling me right there. So let's go to our next example. And this I'll call 2 here. And we're asking, what is the direction of the velocity vector? So what are we given in this situation? So what we're given here is that we have a magnetic field that's pointing into the page. And this is my magnetic field. And I know that the magnetic force is then going to be upwards, like that. So we want to do the same thing here. So now let's go to method 1. So if I use the finger method, here's what I have. I have this guy right here. And if I'm going to use my hand, I'm going to call this method 2. And I will insert method 2 right here. So now let's contrast these guys. So the first thing that I note here is that I see that the magnetic field is pointing in. Well, right here is my middle finger right here, and it's pointing towards the wall right there. The other thing that I note is that the magnetic force is going to be along the direction of my thumb. So the only conclusion here is you're seeing that my finger here is then pointing to the right. So in this situation, you're seeing that my finger is moving in that direction, and that's the velocity right there. So what does it say here with my method 2? Well, look at my fingers. My fingers are pointed towards the wall. But where's my palm? You could see here that my palm is pointing upwards right here, which then tells me that naturally my thumb now is moving in this direction. And so that's the direction of the velocity. Both methods calculate the exact same value. So now if I look at this thing, here's what I'm seeing. Our situation is that we had a magnetic field that pointed into the board. I had a magnetic force for a positive charge that pointed up, and now we see that we have a velocity by the right-hand rule going to the right. So when I look at how does it wrap around the magnetic field lines, well, we can come in here and we could type in, not type in, but draw a couple of the field lines. And so what I'm looking at is that what direction am I actually seeing? So I'm going to pick one point along here, and I'm going to pick this point right here. And when I look at that point, oops, I picked the wrong point, excuse me. I picked a point here, and I know that my velocity is going in this direction. And so then the magnetic force is forcing this guy to push upwards like this. So if I'm pushing this upwards, let me be careful how I push this thing. How about if I draw it here at the tip? So if I push this at the tip right here, you're seeing that the field must be rotating. I mean, the charges must be rotating in a circle like that. I hope I got that right. And it looks like I did. So that's how I'm seeing this. So what does this look like mathematically? So mathematically, I'm seeing this. We set the right-hand coordinate system as this way. So I want to pick a different system. So this time I'm going to say that this guy is now pointing inwards. So this is the direction of the X direction. So then my right-hand rule is then going to make that positive Y, and this guy is going to be positive Z. So now if I apply that to our situation, you could see here is that you could see why I picked that coordinate system, because now I see that my B vector, right, my B vector is going to be in the positive x direction. So now if I look at the magnetic force here, you could see that the magnetic force is in the positive y direction. So then in this situation, we're seeing that the velocity in here has to be to the right. But if we look at the right-hand rule, the right-hand rule really says this, that I have f of b, which is equal to f of b y hat. And so as I have that, this should be equal to my unknown, and my unknown in this situation is q v, and we're going to cross this with the vector that I do know, which then has to be b in the x direction here. So the only way you can get this to be positive is that this guy right here has to be in the positive z direction. So then this implies here is that the only way to make this true with the positive signs is that if v is equal to v in the z direction, so in other words, this guy is in the positive z direction. So now we're going to go to our next situation. And you can see that I'm just, going through this process of trying to get multiple variations. So what is the direction of the magnetic field? So our situation this time is that we have our magnetic force coming out for a positive charge, and we're going to have the velocity going to the left. So let's bring out each of the images. So here's image 1. And let me get image 2, which is right here. So now let's apply our situation. What you're seeing here is that in this situation, you can see here is that this is the direction of the magnetic force in method 1. The palm here is the direction of the magnetic force. So when I look at the index finger, we see here that that's the velocity. And in this situation, in method 2, it's the thumb that's the velocity. So in each situation, you could see here is that it automatically tells us that the magnetic field must be downwards. So then picture-wise, what do I see? I see here that I have a magnetic force like this. I have a velocity like this, and now I have a magnetic field like this here. So when I go to look at my pictures, what am I actually seeing here? Well, I have a magnetic field that's pointing downwards here. We know that they're going to wrap around like this, but what direction are they wrapping themselves in? Let's start with the top view. So I have my field lines. So I have to pick a point that's going to make sense. So if I pick a point up at the top here, what I'm seeing here is that I have a charge that's moving in this direction, but now I have a magnetic force that's going to change this direction where it's now going to move in the counterclockwise direction. So in our situation, we then see here that these lines have to move in the counterclockwise direction relative to us. And so that means here, so when I'm looking at a picture right here, and I have a charge right here, I am actually seeing a magnetic force line pushing it so that it goes in the counterclockwise direction like this. Mathematically, what are we looking at? We want a good coordinate system. So I want to pick one of the axes to be in the direction of the magnetic force and one direction to be in the direction of the velocity. So if I pick this to be my x-axis, then my right-hand rule then says that then one choice here is to pick this to be positive y, and this guy will be positive z. So now if I apply this to our problem, we then have this situation. We have our magnetic force, and this magnetic force will then point in the positive x direction. The velocity is in this direction. That's going to be in the positive y direction. So then when I go and I look at the right-hand rule here, it's going to read something like this. For the magnetic force, this is going to be F of B x, and then I know what my velocity is, so that's going to be QV in the y direction, and then I got to cross this with my B vector, and the only option I have here is that this guy has to be in the positive z direction. That's the only way you're going to get a positive x. Therefore, it has to be in that direction right there. So we now know from the right-hand rule that this is telling me that B has to equal to be in the positive z direction. Now let's look at a couple of things before we leave the direction. So here's a check question. And when I look at this question, I'm just arbitrarily picking points to see if we could make, if anything is possible or if all of them are possible. So imagine that we have three situations. Okay, so we have three situations. And what we want to do here is determine whether the orientations of these vectors are possible. So let's pick our first choice here. So let's say I have a magnetic field that's pointing into the screen. I have a magnetic force that's looking like this. And I'm going to have a velocity vector that's moving in that direction right here. So note that these guys are not all together. So the first thing that we got to do is that we got to put them all together. We got to put all their tails together. So I have my magnetic field here. I have my charge and velocity moving in that direction. And then I see here that I have a magnetic force in that direction. Now note that because of the cross product, everything must be perpendicular. So when I look at this thing, I could see that QV is perpendicular to the magnetic field, but not the magnetic force. In other words, that force should have gone where? It should have been perpendicular in this direction, but it's not. So this is not possible because the magnetic force is not perpendicular to V, Yeah, it's not perpendicular to V. It's perpendicular to the magnetic field. By the way, I did not put the magnetic field in there. Okay, let's look at a different situation. What if I have, again, let's just arbitrarily, I'm just trying to randomize these things. Let's say I have something like this now. And then I keep my same direction for the charge moving in that direction. So once again, this is crazy. We have to put all the tails together. So if I put the tails together, then I'm going to have this guy. That's going to be my magnetic force. And then my magnetic field is going in that direction. And then my velocity is off in this direction again. So the first thing that we should do is that there is a possibility of the charges having components, the velocity having components. So what I'm going to do here is that I'm going to break up the velocity. And so that's my coordinate system. And so what this tells me here is that if I do that, then I have a situation where I have my magnetic force. I now have a component that's going to be perpendicular. Let me move this over here. I have my magnetic field moving in this direction. But now I also have my parallel component moving like that. So what we're seeing here is that the result of that, the parallel component, of course, cancels out. So this is really the same thing as B, the magnetic force, and this guy looking like this. So this is definitely possible. So this is possible. So if I played the same game as I did with where I just randomly pick these guys, let's say that now I have my charge and velocity moving like that. I have a magnetic force like this, and let's say that I now have a magnetic field in this direction. So again, I have to make sure that I put all the tails together. So I have this, which will be QV. I have a magnetic force that's moving like this. And I have this guy, which is B. And right away, you could see that the force is not perpendicular. The force has to be perpendicular to B as well as to V. So if I had a field that was perpendicular like this, then it would be possible. So for the same reasons as we did of the first one, this is not possible. Because f of B is not perpendicular to B. So let's look at, let's practice the left-hand rule. So this is, we're going to look at negative charges, and we're going to go a lot faster here than we did with our previous situation. So what we want to do here is that we want to determine, again, we want to determine the directions of the missing one, assuming, let's pick just a general coordinate system. How about if I say that I'm going to pick a coordinate system like this, and then the right-hand rule, let's make sure that's right, X, Y, Z. Yep, that is a correct one. So this will be in the plus Z direction. This will be in the plus X direction. So what about the direction of f of B? But now we're talking about negative charges. So let's say that I have a magnetic field that goes into the board, and I have a velocity that's moving down like this. What is the direction of a negative charge here? So if the velocity goes down, a positive charge would go to the right. But if I use my left-hand rule, I can immediately see here that I'm going to have a force going to the left for a negative. I'm using the left-hand rule in order to do that. So in this situation, we're saying that the magnetic force direction for the negative here, according to our signs here, should be in the positive y direction. So if I'm looking at this, we could see here is that I have a magnetic field line right here. And so this guy, if I pick one point, let's say I pick a point right here, this is going to experience a magnetic force in this direction, which means that this guy is going to circle around the magnetic field lines in this clockwise direction. What about the direction of, let's say, the velocity? So in this situation, we have a magnetic force pointing inwards, and then my magnetic field is pointing upwards like this. So according to the right-hand rule, I'm going to have a force that has, excuse me, not a force, but a velocity vector that points, let me make sure here, it points to the, into the board. No, that's the force I'm talking about. That velocity should be to the left here. So if I look at the magnetic field lines, we could see here that if I have a collection of field lines, this guy is going to look, it's going to wrap around these lines like this. So in this situation, we have a velocity that's going to be in the positive y direction. And then finally, we're looking at the direction of the B field for this situation where I know the direction of the velocity is going into the board, and I have a magnetic force to the right for a negative charge. So if I'm looking at this guy, this tells me a positive charge would go up, but a negative charge would be the magnetic field would be up for a positive charge, but for a negative charge, it's then going to have a magnetic field down like this. So again, if I look at my field lines, they have to, the charges are going to wrap around them. And so I'm going to say here that they are going to move in the clockwise direction here. Now, how do I know that? If you have a top view of this, no, let's just leave it there. So then I'm going to say that the magnetic field direction is then going to be in the minus, according to our sign convention, is going to be in the negative z direction. So one last two things that I want to do before I finish here is that I want to remind you that this is all about circular motion. So I wanted to draw the field, the complete field, if I have a uniform magnetic field. So what I'm going to say here is that assume a positive charge enters a uniform magnetic field. And the way it's going to enter here is that I'm going to say here is that I'm going to have a magnetic field that goes into the board, and this velocity is going to go in that direction like that. So I know that this velocity here is perpendicular. So what do I expect from this? So what I want to do here is that I want to draw the full motion of this charge. So this is very similar to a ball attached to a string that's moving in a circle. So if I was to give an analogy, what I'm seeing is that, so this is a ball on a string, and we're going to be looking at a top view. So if I look at this thing, I could imagine that I have a circular path. That's going to look something like this. And I imagine that this is the center, and then I'm going to track this red ball as it goes all around this circle here. So if this ball is moving in this direction, what I'm going to find here is that I have tension that's going to change the direction of that ball. And so what happens to the ball? It's going to start to move along this circular path. So when it gets over here to the top image, I still have tension, but that tension is perpendicular and it causes this ball to rotate in that direction. So if I start to draw the whole picture, you're seeing that as long as the tension is perpendicular, this ball is going to move in a circle. The exact same thing happens in a magnetic field with a charge. So if I have a charge that looks something like this, and I'm going to say that this is a uniform magnetic field, so typically what I do here is that I'm going to pick one point, and I'm going to pick this point, and that tells me that the magnetic field is pointing into the page. So now I got to pick one point. So when I look at this point here, I know this is going to move in a circle. So I'm going to try to draw a circle of this guy. Assuming that this is somewhat symmetric. So then here's my center right here. And now I'm going to pick one point for my charge. So what's my one point? I'm going to assume that this is my charge right here. So when I look at my charge, I know that this is a positive charge. And at this moment, it's moving in this direction. So what happens? There's a magnetic force. So if I look at the right-hand rule then tells me I'm going to have a magnetic force in this direction right here. As a consequence, it forces that charge to then start bending. And you could see that if I pick points along this circle here, I am going to have a magnetic force that's always perpendicular and moving towards this and pointing towards the center. So as I look at this guy, I am seeing a circular path because the magnetic force is always perpendicular to the velocity. It doesn't change the speed, it only changes the direction. So in this case, we can see here that the back view from the magnetic field here, that this is now going in a counterclockwise direction. Now, the one thing that I can do here is that I can do the exact same thing for a negative charge. So if we instead have a negative charge, the rotation would be counterclockwise.